Hello everybody. So to continue on our discussions with in the frequency domain specifications. So what we had seen last time were few very basic things that okay, why is this analysis important for us? The first part is that well, I can see how my system behaves at different frequency signals, right. This will also help me, as we saw, in terms of sensitivity of my system, sensitivity to disturbances, sensitivity to noise and so on, and these signals occur at different frequencies. We also saw that if the input to a linear time invariant system is a sinusoidal signal, the output is also a sinusoidal signal. The only difference would be that the magnitude would change, and the change in the magnitude which would depend on what is sitting inside my transfer function, and also the phase shift which is observed, and that phase shift is again depending upon the transfer function or the angle of the transfer function. Then we characterized few things which we call the resonant peak, we had characterized the bandwidth and so on, and all this were very beautifully again related to the system specifications like the damping coefficient, the natural frequency and so on. So we still didn't worry about stability while doing that, because we were just dealing with second order systems, and the kind of systems which we were dealing with in second order, we always know that it is stable, right. When we write omega n square plus s square plus 2 zeta omega n plus omega n square, we know it's always stable. Okay, so what do we do if I have a system which has more than 2 poles, say 5 poles or 6 poles? So today we'll try to answer few of those questions with the help of some frequency response plots. Okay, so these plots are what are called as polar plots. Okay, so what is a polar plot? The polar plot of a sinusoidal transfer function. Again, this is important, and why we know why in the steady state analysis in the frequency domain we just replace s with j omega, because after all the transients die out, only the sinusoidal components remain, and we had a little derivation also of that last time. So we are actually plotting the magnitude versus the phase angle as the frequency is varied from 0 to infinity, right. Okay, this polar plot, well, it's also known as Nyquist plot. The only thing we have to be careful in Nyquist plot, as we will see shortly, is that well, we also deal with negative frequencies, and I'll tell you why that is important. Okay, so why do we need this polar plot? So advantage is that it depends, it depicts very nicely the frequency response characteristic over entire frequency range just in one single plot. Just one graph will tell me what happens at 0 frequency till infinity. Okay, but then I really wouldn't know the contributions of each of the individual factors of the open loop transfer function. I just look at everything as one single block and just one single graph. Okay, nevertheless, there are still lots of nice things which we could do. Okay, so starting with some very basic transfer functions. So an integral factor, right, which has a transfer function over 1 over s. The polar plot, I just write down the sinusoidal transfer function, which is 1 over j omega. It is just the negative imaginary axis. Okay, why is this true? When I just say omega equal to 0, well, I have a magnitude which is well at minus infinity. Okay, and as omega tends to infinity, my magnitude goes to 0. Okay, and since it's just 1 over j omega, my angle is always over here, right. I am always on the imaginary axis. Similarly, I just take the derivative factor of just a pole, which just s is a transfer function. The sinusoidal transfer function becomes just j of omega, and this is just the positive imaginary axis, as you would see, right. So as omega, when omega is 0, the magnitude is 0, and it keeps on increasing as omega goes to infinity. You may ask, sir, this is not a good transfer function because the number of poles are less, or there are actually no poles, there is just 1 0, not physically realizable. Okay, all that is okay. I'm just giving you a little indication of how these things look like in the frequency domain. Nothing about saying that this is a transfer function. Therefore, I don't even call it transfer. I just say it's just a derivative factor, right? M of j omega, j when omega is 0, I have a magnitude of 0, and I just keep on keep on increasing with frequency. Okay. Actually, this omega equal to 0 should be somewhere here. Okay, I'll just correct that. Okay, so something else, right? Now this looks a little more useful, right? Because I can realize this system, and what this system is, that it's just a simple RC filter. I can just draw a little circuit diagram for it, just for us to make a little sense. So I have a R element. We have done this while we were deriving basic transfer functions. So I have a R, I have a C, the input voltage here, and the output voltage here. Okay. So I will not derive the transfer function, but I will assume that you know this, right? So I'll just directly write down the sinusoidal transfer function, not even the overall transfer function. So this M with j omega, it looks like 1 over 1 plus j omega t, where t is the time constant, is t equal to RC. Okay. Now again, I am interested in how this guy moves. This is a complex number, right? It will have a magnitude and a phase, or a phasor, right? How will this guy move or change as the frequencies go from 0 to infinity? Okay, so this guy, I can write this in terms of the magnitude as 1 over square root 1 plus omega square t square, and the angle would be the negative of tan inverse of omega t, right? This is the, we'll call the magnitude m, and this is the angle phi, right? Okay, so let's observe what happens. First is when omega is 0, right? It's just a DC signal. When omega is 0, the magnitude m, I'll just omit the mod symbol, it should be obvious. The magnitude is 1, okay, and the angle phi is 0, right? Just put omega equal to 0 here and here, and that's obvious. Okay, so at omega equal to 0, I just have a phasor which is 1 angle 0, magnitude 1 angle 0, angle 0, my horizontal axis is my reference. Therefore, this will be this one, right? So here, so this will be the entire thing when omega is equal to 0. Okay, now let's do the other extreme. What happens as omega goes to infinity? Okay, as omega goes to infinity, what happens? As omega goes to infinity, what you see is that the magnitude goes to 0 and the angle phi becomes minus 90, right? The tan inverse of negative tan inverse of infinity is minus pi by 2. So I have a phasor which looks like 0 with an angle minus 90. So it will just be some tangential here, right? This direction, this one. Okay, so this is 0 angle minus 90. Okay, so third thing is what happens when omega is 1 over t. In that case, you can compute the magnitude m to be just 1 over square root 2, and the angle phi is minus 45. So I'm just looking at a phasor which I want to plot, 1 over square root 2 angle of minus 45 degrees. That's this one. Right? At omega equal to 1 over t, the magnitude is 1 over root 2 and the angle is negative of 45 degrees. Okay, so if I just keep on computing for other values, I just see that this plot just looks like a very nice semicircle. Okay, so from omega 0, I am here, I increase, so all the plot travels this direction, omega is infinity, it just stops here. Okay, so I'll tell you why we are actually doing these plots, but we'll just do some other interesting plots before we even try to understand why we are doing this. Okay, so this guy, I just add a pole to the previous transfer function. So what do I get here is, well, let me see how I can analyze this. So I have g, or sorry, m of j omega is 1 over j omega 1 plus j omega t, right. I just do the rationalization, right, which I learn in school. So I just multiply and divide this by 1 minus j omega t, 1 minus j omega t. Similarly for this guy, I just multiply in the numerator by j and the denominator also by j. Just that I just get rid of the j in the denominator this way. Okay, so while doing this, so I just get this one, right. If I split up the real and the imaginary parts, I have minus t over 1 plus omega square t square as my real part, and the imaginary part j 1 over omega 1 plus omega square t square. Okay. I just do the computations and I say, well, what happens first when omega is 0? Okay, so when omega is 0, the magnitude becomes minus t, okay, and well, this guy blows up to infinity, right. So I have some complex number which looks like this, minus t minus j infinity, okay. So okay, what I am interested in, how can I write this as a phasor, right? How can I write this as a phasor in terms of its magnitude and the angle? Okay, so let's look at it carefully, right? So magnitude, if I have a complex number a plus jb, the magnitude is square root of a square plus b square. So look at this closely. So the magnitude is actually infinity, okay, and the angle is tan inverse of the complex part over the real part. So tan inverse of infinity divided by t. So that would just be minus 90 degrees. Okay. Okay. Next thing, when omega approaches infinity, when omega approaches infinity, well, this guy becomes 0. Okay, let's skip this minus for 0 minus j 0. So this looks like a phasor of 0 and an angle of minus 180 degrees. Okay. So at omega equal to 0, right. So somewhere here, right. So I just cannot plot that because I will never reach that. At omega equal to 0, what happens is, well, I have a magnitude in the real part. So all this, so I can just split this into the real part and the imaginary part, right. Just given this, just looking at this complex number over here. So the real part has a value of t. Sorry, this should be just t instead of 1 over t. This is just t. Sorry about that. So the real part goes, or it touches this line minus t asymptotically. Okay. So this is the phasor, minus t minus j infinity. So at infinity I am at this one, I just asymptotically touch this line, right. The real part is t and the imaginary part goes to infinity. As omega goes to infinity, I can come back to the origin, right. So somewhere here, right. So 0 and minus 0 at an angle minus 180, right. So this is how the plot would look like for increasing omega. Okay. So these are just the two things. So it's a little okay to understand from here, right. We just write down this explicitly as the real part and the imaginary part and compute these guys. Okay. So the next thing, what happens if I have two poles, 1 plus j omega t1, 1 plus j omega t2, and just be careful when you do this polar plots, is that your transfer function should always be in the time constant form, not like s plus 1, but something like j omega t1 plus 1 and something. That should be very easy to derive, right. We are not going into the derivations of those things. Okay. So my m of j omega 1 plus j omega t1, 1 plus j omega t2. Okay, so this guy has a magnitude, is just the magnitude of this times the magnitude of this, right. So this is square root 1 plus omega square t1 square square root 1 plus omega square t2 square. Angle would be phi is minus tan inverse of omega t1 minus tan inverse omega t2. Okay. Now again I could do the rationalization and all. I can write it down in the real and the imaginary parts, and it would look something like this: 1 minus omega square t1 t2 over 1 plus omega square t1 square 1 plus omega square t2 square minus j omega t1 plus t2, again the entire denominator, 1 plus omega t1 square 1 plus omega t2 square. Okay, so let's do all the steps again. First, what happens when omega is 0? When omega is 0, I just get that the magnitude is 1 and the angle phi is 0, or I am just looking at a phasor, 1 angle 0, it's this one, right? At omega equal to 0, I am just here. Okay, just this point, not the horizontal axis, right? I am just interested in this point. Therefore, this line is not in dark blue color, this one. Okay. Second, what happens when omega tends to infinity? Well, omega tends to infinity. What I see is that, well, this naturally goes to 0, and the angle phi is, well, minus 90 for this guy, minus 90 for this guy. That would be minus 180 degrees. Okay. Now I'll ask myself few questions which we could have answered even earlier, but well, for some reasons we did not, because they were not important in that. So first thing is, does the polar plot touch or intersect the j omega axis? Right, a valid question to ask. So how do I say this? So let's say there is some point here which it touches. At this point, the real part goes to 0. Okay. So look at this expression, right? So does the real part go to 0 for any value of the frequency? So just equate this real part to 0. So what you get is 1 minus omega square t1 t2 is 0, or omega is 1 over square root of t1 t2. Okay. So this is how, and then you can substitute omega. Omega is 1 over square root of t1 t2 over here, and what you get is that the magnitude or the magnitude of m of j omega at omega is 1 over square root t1 t2 is simply square root of t1 t2 over t1 plus t2. This could just be easily obtained by just substituting this in the expression for magnitude. That's marked here, right? So this is omega is 1 over square root t1 t2, and this magnitude here is this much, and then again as omega goes to infinity, you again reach the origin you arrive at, if I use the root locus terminology, arrive at an angle of minus 180 degrees to this point. Okay. So again the same steps. Look at the magnitude, look at the phase, just compute simply what happens at omega is 0, omega is infinity, just check if the polar plot touches the j omega axis. You could also check, why don't we, you may also ask, why don't we see intersection for the real axis somewhere here or here. That you could just check by computing or equating the imaginary part to 0, and you will only get the solution that it only touches this guy at omega is equal to infinity and omega equal to 0. That you can just check from these things. Okay. The next thing. Okay. So what if I add a pole at the origin to the previous transfer function? Okay. So how does this go? So this is just the previous guy to which I add j omega. Okay, let's do some simple computations before. When omega equal to 0, I can easily see that the magnitude m goes to infinity. Okay, when omega is 0, this guy does not contribute to the angle, this guy does not contribute to the angle, only contribution comes from this guy, that is as phi equal to minus 90. Okay, it's similar to what we had in the second example, right? The magnitude becomes infinity and phi is minus 90, right? So this one. You also see that this number which was earlier T1 is now T1 plus T2. Right? So here, right, it was just T. Okay, now it has just become the sum of these two, T1 plus T2. Okay, then what happens to this plot as omega goes to infinity? At omega goes to infinity, the magnitude goes to 0. Okay, what is the angle contribution as omega goes to infinity? Well, it will just be phi would be minus 90, right? Because okay, this guy has a minus 90 minus, sorry, it will be plus 90, minus 90, minus 90, minus 90, it will be minus of 270, and therefore you see, so everything is infinity, right? Tan inverse of infinity, tan inverse of infinity, tan inverse of infinity, because all with a negative sign, because these are poles, and you have minus 270 or even plus 90. So this is what happens here, right? I can also see now, does this intersect the real axis? Okay, so this can be obtained by setting the imaginary part of m j omega to 0. Okay, so well, I'll just skip those expressions, right? So you can easily just do this, right? So this to this magnitude, what you do is just add 1 over j omega. Okay, so you can just see, right? So if I add a 1 over j omega, so this guy will become my imaginary part now because of this j. Okay, let's just quickly do this. How does the imaginary part look like? So this imaginary part is just the real part of the previous guy, 1 minus omega square T1 T2 divided by again 1 plus omega T1 square, 1 plus omega T2 square, and I just do a 1 over j omega. This will also be similar to writing, so I just get rid of the j from the denominator. I'll just have a j in the numerator with a minus sign. Okay, again, when does this go to 0? This goes to 0 when omega is 1 over square root of T1 to T2. Okay, now substitute this omega in the real part to get the value. Okay, I'll just leave that simple computation to you. Okay. Okay, so based on these things, we can just keep on adding, one more pole here, j omega square, and possibly add a 0 here, and then just keep on doing bunch of things. But okay, we'll just stop here. Otherwise, we'll have to spend few years doing all those plots. Okay, so let's see what do these plots mean, right? And what do these plots mean? And then can I infer something more just than saying, oh, what happens at omega equal to 0, what happens at omega equal to infinity, what is the angle, what is the magnitude, and so on. Okay, so Nyquist gives us a nice answer. So before we do that, let's just do some stuff. Okay, so what do we know now? We know this for a long time now, that stability depends on the roots of the characteristic equation. Okay, that the roots should be, or the poles should be on the left half S plane is what the transfer function stability criterion tells me. Okay. Now this Nyquist stability criterion, it determines the stability of a closed loop system from its open loop frequency response characteristic and also its open loop poles. Okay. We will all today what we will do is just to see what this statement means. Okay. So again, what does this do? It relates the open loop frequency response. Okay. So again, all the analysis, this is important because I just look at the open loop transfer function g times h, and I can tell you what is the closed loop behavior, right. So that's what Nyquist will tell us very shortly, right. The Nyquist plot relates the open loop transfer function, open loop frequency response to the number of poles and zeros that lie in the right half S plane of the characteristic equation. Okay. Now we see how we arrive at this. Okay. So just consider a function q of S, right, which is again in the usual terms you can say it's a transfer function which has m number of zeros, n number of poles, and usually these n is greater than or equal to m. Okay. Okay. So what is S here? S is a complex variable, real part sigma, imaginary part omega, right. If this is complex variable, the function qx is also a complex variable. Okay. Let me call that u plus jv in the new axis. So I start with the sigma j omega axis and I go to sigma jv axis via this map q, right. So q takes S, it computes all these things and gives me q of S. Okay, not complicated, don't get worried, right. So what does this mean? That for every point S in the S plane, so if I take, okay, so let me just see here, right. So this is my S plane. So for every point here S, let me call this S1, there might be a corresponding point Q of S1 here. Not there might be, there will be, right. For all the points as at which QS is analytic, where I can actually compute this, right. Or so okay, we'll not go into the definitions of analytic functions, but we'll just say that well I can compute it almost at all points except when Q is analytic, right. So for S1 there will exist a Q of S1. Similarly, I take a S2 here, there will exist a Q of S2 here, and so on, right. So whatever points here, I'll have some corresponding points here, and here, right. So the function Qs, this maps the S plane. So this is my S plane and this is via Q of S, and this function Q maps the S plane, which I call sigma and j omega, to the QS plane, right, with maybe coordinates I can call u and jv, right. So this is what this particular expression tells us, right. This is nothing surprising and nothing new. Okay. So we can just say, oh, well, we avoid points like S equal to beta 1, right. That time Q of S may not exist. So we avoid all those points, okay, or what we call as singular points. Okay. So that's what I said. So the contour in the S plane which does not pass through any singular point, there corresponds there exists a corresponding contour in the QS plane. The contour is like this guy, right, this entire map which I take here, right. I just take this little closed loop here and I say that something else happens here. Well, I just may have to make sure that I don't hit a point where S equal to beta 1 or S equal to beta 2, or I don't hit S at the poles, and because at that point Q of S is not defined, but for all other points it is defined. Okay. We will not necessarily be interested in the shape of the contour, right. We'll just say there is a contour here which maps to a contour on the other side. Our aim here is to detect if there are any poles of the closed loop system in the right half plane. And when I detect this, I have, there is direct implication on stability. So I do a trick where say, well, I ask myself a question, does there exist a pole on the right half plane? I do a graphical technique, answer is yes, system is unstable. Answer is no, well, system is stable, okay. So let's just ask few questions, right. What does it mean when the QS plane encircles the origin, right. So this is a little important here, right. So why okay, I am not really interested in the shape, it could be this one or it could just be something, I am just interested in this origin. Does the contour on the QS plane contain the origin? Not necessarily here it could be whatever. I'll tell you some other stuff related to this now. Okay, now let's start by considering the case when the S plane contour encloses only one of the zeros of QS. So what does that mean? So Q of S has m zeros, and let's say that this guy encloses 1 0. Okay, so let me draw a 0 here and I call it as alpha 1. Okay. So all the other poles and zeros are outside the contour. Okay. Now, given this complex number, I can compute the magnitude of QS as blah blah blah, and I can also compute the angle, right? The angles of the zeros minus the angles of the poles. Okay. So let's see here. So this is the contour in the S plane which encircles a 0, right? Okay. So let's see, as the point S follows the path in the clockwise direction. Okay, now let's see, right? So I am here and I just take a clockwise direction, I come all the way and I just end up here. Now with respect to this, I am just say looking at this particular phasor, right? What does this do? This actually has to rotate all the way and come back, which is it does a net angle, or it generates a net angle of minus 2 pi, because the positive angle we measured as the anti-clockwise. Okay, now what does this do, right? This angle from the pole at beta 1, well, it goes here, this phasor goes here, 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 and again comes back here, right? So it just goes this and just comes back this, right? It just goes this and comes back this, whereas the other way it just starts here and does a complete revolution like this. Okay. So the pole just does this and just comes back over. So this, how much angle does this generate? Well, the angle is 0. Similarly, this guy again just goes again and again comes back to same position. It just doesn't really take a revolution or a rotation. Similarly with alpha 2. Okay. So alpha 1 generates, or the phasor S minus alpha 1. So if I just was to mark this guy would be the phasor S minus alpha 1. Okay. The phasor S minus alpha 1, possibly I can write it here just to, it generates an angle of minus 2 pi, while all other phasors generate 0 net angles. Okay. Okay, carefully we will go to the next statement. What does this mean? That QS phasor also should undergo a net phase change of 2 pi. Okay. So something like this, right? If I take a QS here, I know that Q maps the S plane to the QS plane. So if S undergoes a phase shift of 2 pi, right? So this also should undergo a phase shift of 2 pi, just from the expression of QS. Okay. And the tip of the QS phasor, which is this guy, it describes a contour about the origin. What happens when S equal to alpha 1? This is the origin. So this guy maps to the origin here. Okay. So again, I have here 2 zeros, alpha 1, alpha 2, 2 poles, beta 1, beta 2. I just I just pick this guy alpha 1 and I just generate a contour along this in the clockwise direction. So I go here, I see that this guy also generates a contour, right, a closed curve again in the clockwise direction, right, and then I can just measure this phasor and also the angle again, that's just from the alpha 1s and beta 1s and beta 2s. Okay, not only that, if I am encircling a 0 here, 0, I will encircle the origin here. Okay, that is because when S equal to alpha 1, my map, what does Q of S do? When S equal to alpha 1, it maps to the origin. Okay. So that's a very simple way of understanding this. There's actually a much complicated proof from complex analysis, which we will not go into, but we'll just learn what complex analysis is telling us. We'll just believe what people from complex analysis told us, but we will just use it in our own way, right? We just be a little smart and translate into our own language and say, oh, okay, well, this information which they proved is correct will actually help me in my stability analysis. Okay, so what happens when my contour encloses 2 zeros? Okay, so let me just draw this, say there is a 0 here, there is a 0 here, and I just go around this. So this is my S plane. with sigma and j omega. So what will happen here is that I will encircle the origin twice, once like this and once like this, maybe something like this. Again, not the shape is not really important. What we are interested is in the encirclements of the origin. Right, so you have a u and jb. Okay. Similarly, if there are n zeros, I will encircle the origin n times. Again, if this is clockwise direction, this is also the clockwise direction. Lastly, if the contour does not enclose any pole or 0, as I said earlier, say if I just here, I'll just be here, right? I just not trouble the origin. If I'm just here, I'll just be here. Nothing happens. It will never encircle the origin. That's just what the Q map tells me. Okay. Now what about encirclement of a pole? Okay. So let's say again I do the same thing. I just draw it for our purpose here. So let's say I have a pole here. This was my beta 1. Then I had a pole here earlier. This was beta 2. I had a 0 somewhere here and a 0 somewhere here, alpha 1, alpha 2. Okay. Now again let's say I am just having a contour where I do this, right, this guy, and I start from here, right. So this phasor is my S minus beta 1. Okay. So what happens again, let's see all the angles, right. If I am starting from here, this is my point S, and say there is a phasor from here, there is a phasor from here, and the phasor from here. Okay. Now how does the phasor alpha 1 change, right. If I just draw this pen, the phasor alpha 1 and the clockwise, it just goes here or traverses all the way and just be here, right, again, which means it generates an angle of 0, right. So again just look at here, it goes here, here, and again comes back here. Similarly, beta 2 contributes an angle 0, alpha 2 also contributes an angle 0. Okay, what is beta 1 doing? Beta 1, okay, it's in this position, it just goes again all the way this way, right. Again the phasor S minus beta 1, I will just do this here, it generates it traverses an angle of minus 2 pi as S traverses along a closed path. Okay. Therefore what will happen here is that QS will now have an angle change of 2 pi, say somewhere here, and this is plus 2 pi because S minus beta 1 occurs in the denominator, right, it just goes up, and you see that the angle always becomes a minus when I am talking of the angle of a pole, right. And this means again I just encounter or encircle one, I encircle the origin once in the counterclockwise direction now. Okay. Again we will not really see why exactly we are encircling the origin, it is based on the same arguments as before, right. Okay. So what we will just try to understand is the following, that if in the S plane I encircle a 0 in the clockwise direction, the corresponding contour in the QS plane encircles the origin once in the clockwise direction. If there are more than 1 0, say 5 zeros, I will encircle 5 times. If I am encircling a pole in the clockwise direction, correspondingly in the QS plane I will encircle the origin once now in the counterclockwise direction, because I am looking at the pole, right, which contributes an angle of negative when it goes to the denominator. Okay. So therefore I can just say something more now. If there are p poles and z zeros of QS encircled by the S plane, so let's say I just draw this and I say, and I am not really interested in where these poles are, they could be stable, they could be unstable on the imaginary axis, at the origin, whatever. I am not talking of stability at all. I am just saying, well, so say there is a pole here, a 0 here, a 0 here, and say one more pole here, right. And I say I just want to have some fun, and I say I just enclose this all the time. I just so in the S plane I encircle all of them, right. So this is sigma j omega in the S plane. Okay. Then the corresponding QS plane contour must encircle the origin z times in the clockwise direction. In this case, it should be 2 times in the clockwise direction, p times in the counterclockwise direction, number of poles. 2 zeros, 2 times in the clockwise direction, 3 poles, 3 times in the counterclockwise direction, and the net encirclement is p minus z in the counterclockwise directions. Right? If this number is, say, well, I mean, I'll always say this number will always be greater than 1 possibly, or even if it is less than 1, it does not really matter, because I am just looking, if it is minus 1 times counterclockwise means 1 times in the clockwise direction. So, the sign will take care of themselves. Okay. So, we now know about encirclements, the mapping from the S plane to the QS plane. What happens if I encircle poles and zeros in the S plane? How does it reflect on the QS plane, right? That I know. Okay. Now, what is the relation to stability? Okay, the standard pole 0 form, okay, I know that my open loop transfer function is GH has again a set of zeros, a set of poles, right? And my characteristic equation Q of S is 1 plus K, again this set of zeros and the set of poles, okay? And I can write this as an equation of the form S plus Z prime till Zn prime. Okay, this number will no longer be M, but it will be N, because this will go here. So, I can just say this is S plus P1 till S plus Pn plus K times S plus Z1 till S plus Zn over, again the open loop poles, S plus P1, S plus P2, S plus Pn. So, this will also be S power n, this will also be S power n. So, this will have n zeros and n poles. Okay. The zeros of Qs are the roots of characteristic equation. So, this is a transfer function with a set of zeros and a set of poles. Qs going to 0 would give me that all this S plus Z1 prime multiplied by S plus Z2 prime all the way till S plus Zn prime should go to 0, and therefore, the zeros of Qs, nothing to do with the plant, nothing to do with G times H now. We are just doing with 1 plus K S K this one and this one, okay, or 1 plus GH, only the characteristic equation. And the poles of Q of S are the same as the system poles, okay. Now, when is this system stable? For the system to be stable, the roots of the characteristic equation, what is the root of, what is the characteristic equation? 1 plus K or K times S plus, okay, what S minus Z1 I think, sorry. Okay, what did we use? Okay, S plus, so it does not matter. 1 plus K, S plus Z1, S plus Zm over S plus P1, S plus Pm equal to 0, or this guy is 0, right? So, Qs, this guy is equal to 0. Okay. So, the roots of this equation must lie in the left half of the S plane. That is all, that is what we know from the earlier lectures. Okay. Now, this roots of the characteristic equation turns out to be the zeros of this Q of S. So, if the zeros is confusing, just leave it. You can just say the roots of the characteristic equation, nothing else. You can, that's why I wrote it in italics. You can just also just not read this. If the term 0, why am I interested in 0 is confusing you, do not read that. Just say, well, the roots of the characteristic equation, that is all. Just that it happens to be, so happens that these guys are in the numerator, right, and then in the numerator terms we always call them zeros. Okay. Then the question arises, what if the open loop system has pole in the right half plane, right, which means that the open loop system is unstable. Say this P1 is at plus 1, does not matter, right. This P1, even if it is in plus 1, I can or I may have all these Z1 till Zn to be on the left half, okay. The expression for Qs therefore suggests that even if the open loop system is unstable, the closed loop system may be stable, because these are the open loop poles and these are the closed loop poles. We will see an example also. So meaning to say that even if the open loop system is unstable, I can make it stable. This is not what Nyquist will teach us how to do that. Nyquist will just tell us is the closed loop system stable or not. Okay. Now what we need to investigate is, are there any roots of QS in the right half S plane, right, or any of this numerator guys Z1 prime till Zn prime, is anyone sitting in the right half plane, right? Is Z1 prime, Z2 prime, Zn prime, is anyone sitting on the right half plane? That is what we will try to investigate, and that is what leads us to define the Nyquist stability criterion. Okay. So now the encirclements will come into picture, now the polar plots will come into picture, and so on. Okay. Okay. So what do I need to investigate? I need to investigate the presence of any right half 0. This is again the right half 0 of Q of S, right. The zeros of Q of S are my closed loop poles. Just you write down that and just try to understand what it means, right. I am not really talking of zeros here. I am just still talking of the closed loop poles which happen to be the zeros of the denominator transfer function 1 plus GH or 1 plus KGH, which is Q. Okay. Now choose a contour completely that completely encircles or encloses the right half S plane, right, and this is called the Nyquist contour. Again it is directed clockwise and comprises of an infinite line segment J C1 with J infinity, and then an arc of again infinite radius, right. Okay. So what happens along C1? Along C1 what is happening is S is just J omega, this is C1, right, just this line. So S is all J omega with omega varying from minus infinity to plus infinity. So this I am starting from minus infinity all the way till plus infinity, the entire imaginary axis. And along C2, what is C2? S is R e power j theta, just the phasor here. Again with theta, what does theta do? Theta goes from here till here or here till here, right, whichever day. If you measure from here to here, you say that theta varies from pi by 2 to minus of pi by 2, right. So this means I am taking care of the entire right half plane, including the imaginary axis. Okay. Now we will ask some questions. First is, why do we need to define a contour? Such a contour, I have to start from 0, go till infinity in the j plus j omega infinity minus j omega infinity. Not only that, I also have to travel r e power j theta with r going to infinity. Why do I need to do this? Well, such a counter encloses all the right half plane, all the right half poles and zeros of my characteristic equation. Okay. Now suppose, everything will now start to make sense of what we did so far. Suppose there are Z zeros and P poles of QS in the right half plane. Again we will just write out. So Z zeros, so zeros of Q of S were S plus Z1 prime, S plus Z2 prime, and so on until S plus Zn prime, and then you have poles S plus P2. These are all the open loop poles. In other words, all these Z1 prime till Zn prime are the closed loop poles. Okay. Okay. So as S moves along the Nyquist contour in the S plane, so this is the Nyquist contour now, right, which you defined as the entire right half plane. Okay. Now as S moves along the contour in the S plane, a closed contour is traversed in the QS plane which encircles the origin. Okay. So let us say, so this is my Nyquist contour. Say it has zeros here, poles here, few more zeros, few more poles, whatever. Okay. Now if I map this contour, what I wanted to go from the S plane. So, this is in the S plane, the Nyquist contour, and I want to see what happens in the QS plane. Okay, this QS plane will encircle the origin, right? That's what I learned from these previous slides here, right? These things, encirclement of the origin. Okay. So, as S moves along the Nyquist contour in the S plane, a closed contour is traversed in the QS plane, which encloses the origin n equal to p minus z times in the counterclockwise direction. Right? That is what we also observed somewhere here. Encirclement of the origin is p minus z times in the counterclockwise direction. Okay. Now what has this to do with stability, right? I am still talking of so many things. I talked of polar plots, I talked from omega from 0 to infinity, I talked of encirclements of poles and zeros, and then correspondingly I said something happening in the clockwise, something happening in the clockwise direction. Okay, now we will see if this actually makes sense, right? Now, how do we test stability with these encirclements of the origin? Now, I will again ask myself a question: when is this system stable? Well, for the system to be stable, there should be no zeros of QS, these guys, in the right half S plane, right? Because these zeros of Q of S are the roots of the characteristic equation, and these are also the poles of the closed loop system. Okay. Now, this system, for this system to be stable, Z should be equal to 0. Okay, there should be no zeros on the right half plane. Okay. Now, this is met if the number of encirclements is p, it is not z, it is n. Okay. Z is anyway 0. So, if the number of encirclements in the counterclockwise direction, right, this is n, the number of encirclements in the counterclockwise direction is equal to the number of poles of QS in the right half plane, right? Because I am just my contour is just the right half plane. So there might be a P1 sitting here, P1, P2, P3, P4 and so on. So if there are 4 of these guys sitting here, then this n should be equal to 4. Okay. If the system or for the system should be stable, there should be no zeros. All this Z1 till Zn should be on the left half plane. So none of them should sit on the right hand side. So Z should be equal to 0. Now if Z equal to 0 and I measure the number of counterclockwise encirclements, what should that match? That should match the number of poles from P1 till Pn on the right half plane. Okay. This means that for the closed loop system to be stable, the number of counterclockwise encirclements of the origin of the QS plane should equal the number of right half S plane. That is what I just explained, right, through these things. Okay. And these are open loop unstable poles. So I don't really worry now, is the open loop system unstable? Oh, well, open loop system is unstable, I can't do anything, so let's close the books and go home. No, there is still hope. If n equal to p, then my closed loop system is stable, right? Okay. And if the open loop system is a nice guy, if it is stable, then the closed loop system is stable if and only if n equal to p equal to 0. So if all these guys are well behaved, right, then there is no p which is on the right half plane, which means this number p here, this number p here will go to 0. So n equal to p equal to 0. So my stability now translates to the number of times I encircle the origin in the counterclockwise direction, right. For example, if all these poles are stable, okay, and say n is equal to 1 or minus 1 to say n equal to minus 1, then my system is unstable, because well there are no poles of all these, the p's are equal to 0, and whenever z is greater than 1 or greater than or equal to 1, then I am unstable, right. I always want z to be 0, Right? This is a necessary condition. Okay. Now n equal to p equal to 0, which means no encirclements of the origin. So in this entire region here, I don't encircle zeros, which I should never encircle. I should never encounter zeros, and I also never encounter poles here. So maybe my contour here, when there are no poles and zeros, might just be here, and therefore I am happy. Okay. So, well, you might say, sir, this is actually too complicated because I start with an expression which already looks complicated. There are m zeros, n poles. I have to compute all this, count these numbers. That might be cumbersome. However, this is actually given to me, right? The plant is given to me. The feedback loop H is also given to me. Right? And what I promised you, or what I told you, is that just by looking at the open loop transfer function G and H, I can tell you the closed loop behavior. But no, well, I actually made you compute all these Z1 primes till Zn primes to see where they are, and then I said something to do with Z minus P, P minus Z, encirclements and so on. But okay, we'll just simplify things a little bit, just to again get you to the point which I promised you, that just by the open loop behavior I can tell the closed loop system stability. Okay, so GH or GS HS. So this is my closed loop characteristic equation, right? 1 plus G times H, and I can just rewrite this as the Q of S minus 1. So this is just my Q of S. I am just rewriting this as Q of S minus 1. Okay. Now this is a complex number. Okay. Just say I am just looking at 0 plus J0, and I am just doing minus 1. So what happens is that the real part shifts with minus 1 plus J0. Okay. Similarly, say I have 1 plus J2. Okay. So I am just doing a minus 1. So what happens is I will just have 1 minus 1 0 plus J2. Similarly, if I just have any complex number, right, sigma plus J omega, I do a minus 1, I will just get a sigma minus 1 plus J omega, right. The imaginary thing always remains the same, and the real part is shifted by 1, right. Just if it's a sigma, it just becomes sigma minus 1. Okay. So if the contour of GH, right, this is the same as the contour of 1 plus G times H, just that I am just shifting the real part to minus 1 plus J0. Okay. I will show you a plot of this, and therefore if I say, well, have I encircled the origin of 1 plus GH, this is actually equivalent to saying, have I encircled, or asking a similar question, have I encircled the point minus 1 plus J0 of GH. So I am comparing encirclements of origin of 1 plus GH to this is minus 1 plus J0 of G times H. Okay. So just show you a plot, right. So this is 1 plus GH. Okay. Now I just shift it by minus 1, right, minus 1 plus J0. This is 1 plus GH, I just do a minus 1. So it just shifts here, which means the origin, which I am interested in, the encirclement of the origin, now I just do a minus 1 all of a sudden. So therefore this origin, so I was interested in encirclement of the origin of 1 plus GH, or the contour of 1 plus GH. Now I am just doing 1 plus GH minus 1. So the origin also shifts here. Oh sorry, I am really sorry. So the plot shifts by minus 1 in magnitude. So you can see all this distance would be minus 1, and then so from here I shift here. Okay. So encirclement of origin of 1 plus GH is equal to encirclement of the point minus 1 plus J0 of GH. Now this is easier to check because I know G, I know H. I don't need to compute Z1 prime all the way till Zn prime. So now all the results of n equal to P minus Z of the origin will transfer to again n equal to p minus z, not of the origin but now of the point minus 1 plus j 0. Okay, now this will be my point of interest. Okay, so let us read the statements. If the contour GH of the open loop transfer function corresponding to the Nyquist contour, if it encircles the point minus 1 plus j 0 in the counterclockwise directions as many number of times as the right half poles of G times H, the closed loop remains stable. Everything remains same, just that the encirclement of origin now just translates to encirclement of minus 1 plus j 0. Everything you just go to the previous slides, replace the origin with minus 1 plus j 0 and you will have this thing. Okay. So, if the open loop system is stable, again I am just rewriting all those things which I said, then the closed loop system is stable if the contour does not encircle the point minus 1 plus j 0. Earlier I said if the open loop was stable, then the closed loop system or the closed loop contour of 1 plus gh should not encircle the origin. Now just say, well, if the open loop system is stable, the contour of gh should not encircle the point minus 1 plus j 0. Just origin, do a control C and then there is a control V, right, or control F and control V, find and replace for origin. So now this is our point of interest, minus 1 plus j 0. Okay, to summarize all these things, we will just, so this is the statement of the Nyquist stability criterion, right. I am just interested in the point minus 1 plus j 0. Okay, so let us just summarize with the help of example, right. Consider a feedback system, his open loop transfer function is this guy. Okay. Now this is similar of a polar plot which we had in one of the earlier slides. Okay, let me slowly go there. This one, right. So, okay, just what I am interested little more in doing is, there I plotted as omega was from 0 to infinity. Now I plot a little more, right. I also am interested in minus infinity, because if I just plot omega from 0 to infinity, I am just looking at this one, this contour, but I am interested in the entire right half plane. So I just do the same thing, right, just look at what happens when omega is minus infinity. Nothing changes, I just have to compute again the angle and the phase, the angle and the magnitude, or the magnitude and the phase. So for this example, well, the infinite semicircular arc, it maps to the origin, the plot of GS. Okay, so this is my origin, somewhere here is the point minus 1, it is not even in the graph, so I am nowhere related to minus 1 plus j 0. So what do I conclude is that the plot of GH, again, okay, sorry, there is some distortion here, I will just take care of this. So this is the plot of GH, right, and then it does not encircle minus 1 plus j 0 for any positive values of k, t1 and t2. Sorry for the distortion, I will take care of this slide. And therefore, what should, so n must be p minus z, open loop system is stable, therefore p is 0, z should be 0 for stability, therefore n should be 0, what, of the point minus 1 plus j 0. But if you look here, I am really far away from minus 1 from j 0, therefore the system is stable. Okay, now look at this example, s plus 2, s plus 1, s minus 1. Okay, this is the open loop system is unstable. Okay, so this is some interesting case now. Now I just draw the Nyquist plot, I just look at what happens at omega is 0, omega is minus infinity, omega at plus infinity, and I just plot this, right. So I start from omega is 0, I am here, and then I just reach here. So I start from minus infinity, I go all the way here, and I go all the way here, and I just plot this and say, okay, where am I? So this is my origin. Here I am at a distance of 2 and this one. So here my p is 1, z should as always be 0, therefore n, which is p minus z, should be 1 in the counterclockwise direction. Okay, let us just check this. Okay, so if I just move in the counterclockwise direction, am I encircling the point minus 1 plus j 0? Okay, so this is the point minus 1 plus j 0. I am encircling it one time, and therefore the closed loop system is stable. Okay, I start with a open loop unstable system, and Nyquist tells me that it is actually closed loop stable, right, with 1 plus 1 plus g times h, I just do the feedback and I am closed loop stable, right. It does not tell me still how can I make a closed loop system stable, can I do it always, none of those questions are answered, just that, well, I can make, or I can start from an open loop unstable system. Nyquist will tell me, well, is it closed loop stable or not, right. So just via these plots. So the polar plot started from 0 to infinity. Here I am even going from 0 minus to minus infinity. That's the only little change, but nothing changes in the analysis. Okay. So what we learned so far is polar plots, and we just started to define for ourselves the notion of stability in the frequency domain leading to the Nyquist stability criterion, did a couple of examples, and next we will do some special cases of the Nyquist criterion, right. What if I hit a singular point, what if there is a pole on the imaginary axis, okay, things like that, and then we will also define. So now everything was to do with minus 1 plus j 0, how far I am from minus 1 plus j 0, okay. So we will define relative stability in the frequency domain and introduce the concepts of gain margin and phase margin. Okay, thank you.